Thank you for inviting me to attend and talk to you guys about something that I'm really passionate about. I study the Earth from space. I'm a remote sensing geoscientist, and this is a talk I put together just really to give you a whistle-stop tour about the scale and breadth of some of the things we can do with the data that are available to us now. So it's by no means comprehensive. Please ask questions later on and find me in the social events and we can go into more detail. So yeah, so this is one of my favorite photos ever. It was the first photo taken from the moon by astronaut Bill Anders. And it's called Earthrise. And it's the first ever image we have taken by a human from another celestial object, namely the moon. And I think it's really beautiful and it sets the setting really for this talk and our view of the world as a whole. And, you know, that's where we started from. But I guess, you know, we now have many satellites in space and they're constantly monitoring the planets and for various things. And so I want to give you a brief introduction to why we need Earth observation satellites. And for me, there's only one real main reason. It's because the Earth is dynamic. The Earth's physical topography is in constant motion and it's always changing. The weather, as you saw in this beautiful image on the left, this is in 2010 when the entire UK was covered in snow. So all these changes require constant monitoring, and satellites enable us to do this. Not just the physical landscape, but the human landscape too. And the scale, I don't think there are many technologies that exist that can take a picture of the entirety of Japan in one shot. So this sense of scale is something you can only achieve by looking down from above. And that's really quite important, I think, when you start looking at large scale things. The regularity and the dynamic data. So most satellites now are in orbit and they continuously, regularly orbit the Earth in mostly polar orbits, so north-south. And so they will come back to the same spot at regular intervals, 10, 15, 20 days, until they'll take another data set. So this regularity enables us to understand how things have changed over time. But also they can be dynamic. So if there's a sort of natural hazard somewhere, an earthquake or a disaster, we can target satellites, say, look, take more images of this particular area because we need lots of data there. So this enables us to be more systematic about the way we collect data and what we'd use the data for. Data consistency, and this actually turns out to be quite an important issue, is if the same satellite comes back and takes an image of the same spot, 10, 12 days data, it's taken this exact same format. The last set of data were collected. And this enables us to do comparisons. And that consistency is really, really quite important to see long-term trends of many aspects of the planet. And satellites enable us that perspective. And for me, this is probably the most interesting because how else could you produce images like this? And this is called the blue marble, and it's a cloud-free, complete composite of the planet, created by collecting all the satellite images and picking the ones that don't have clouds in them and stitching them all together into this beautiful composite of the world we live on. And the satellites enable this to create maps like this that cartographers of the 1500s would have only dreamed about making. And the cost actually turns out to be quite cheaper. So per square meter or square kilometer cost of collecting data from space is actually quite a lot cheaper than physically trawling through many of these places. Not that it's a replacement, it's just an extra layer of data we can add to our studies. So where did it begin? This is the first image ever taken from space. It was taken in 1948 with a pseudo camera stuck onto the end of this rocket. And this is a modified rocket from a German V2 missile. So it's the first image from space. The first satellite into orbit, as many of you will know, is the Sputnik 1, but that didn't take any visual data. It took radio images. This was the first, Explorer 6 in 1959. That was the first satellite to take photographs from space. And it took this rather boring image of a cloud of the Pacific Ocean. And I'm happy to say that we've improved our ability to take images since then. And now in space, we have around 6,000 satellites in orbit at the moment. Over 60% of these are actually not working, they're defunct satellites. 2,000 of these are for communication and around 900 are for Earth observation, which is what we're talking about here. But just as a brief aside, this is a question that I get asked a lot by kids, and I thought it would be quite interesting to briefly mention it. How far away is space? This is quite an important question because the laws that govern space activity is different to the laws that govern atmospheric activities. So it's really quite important to define where space is. And the agreed standard is 100 kilometers above mean sea level. That's otherwise known as the Kármán line. So you may have seen in the news recently that the Virgin Galactic team went up into space, so as the PR team would say, but they only got up to 85 kilometers, so not officially into space, despite what the PR team would say, but still great achievement. And how far is 100 kilometers? So now we're all virtually at the British Geological Survey in Nottingham, and 100 kilometers takes me to Skegness, to the beach. So if I were to get in my car and drive in a straight line to Skegness and do that vertically, I'd be in space. So it's actually not that far at all. So why is it so expensive to get there? It's expensive because of gravity. You have to escape the pull of gravity, and importantly, get up to speed, because otherwise you're just throwing like a football into the air and it will come back down. So you have to get up to speed. How fast? About 17,000 miles per hour to get into orbit. So this is where all the fuel goes in your spaceship, to actually get up to speed, not get out into space. And what happens when you get up there? Well, satellites start observing the Earth. Each satellite has its own sort of viewing mode, and it's a way of collecting data, but they all share a characteristic. They view the Earth along this spectrum. And a couple of examples of satellites. The UK military has a network of satellites that monitor using the radio waves, and that network is called Skynet. So those of you from a certain generation will, oh gosh. But yeah, we have a network of satellites from the military called Skynet, monitoring the Earth. Microwave satellites are the ones that I use a lot, and the weather, every day you check the weather, it's based on microwave satellite imagery and data. Infrared is measuring temperature, so the ocean temperatures on the world and also the land temperatures. And obviously the optical that gives us these beautiful images of the planet. The lower, higher frequency bands, ultraviolet, X-rays and gamma rays, they tend to be more used for looking at the universe at large rather than down to the Earth. So an interesting and important point to note is the resolution. The resolution is the smallest thing a satellite can see. And the old spy satellites, so the Americans were spying on most of the world in the 60s and 70s, and they had a resolution at around 2 meters, which is about the size of a car. So that's what they could see in the 70s. These images have only recently become declassified, so we can all look into them now. But today, the publicly available images can look at something as small as 30 centimeters. That's like an open book. So as an example, this is some of you may remember last year, I think, this tanker got stuck on the edge of the Mauritian coast on the reef. And so this satellite took an image of it. So that's a tanker there. And if we can zoom in, you can zoom in to the satellite, you can see more details, and you can zoom in even more, see the back end of the ship stuck on the reef. And you can zoom one level more as well to see the people moving around on that ship. You also may remember this Ever Given ship that got stuck in the Suez Canal. And this is an image taken from space, 700 kilometers away. This is equivalent of me sitting in Nottingham, pointing a camera and taking a picture of my friend's car in Frankfurt, Germany. So this is the power of resolution, the things we can do now with these sort of images. And what can we do? What's the science we can do with this? So this is a beautiful image taken by the European Space Agency satellite, and it's of the Zambezi Delta in Mozambique. And those of you who study these things will notice that that's the old ancient coastline of Mozambique, and this is obviously the new coastline. And what's happened is this delta, this river has been dumping sand over thousands of years and built out over into the sea. So the physical landscape of Mozambique is changing, and it's growing because this river is pushing sediment out and physically growing the landscape. And I love these kind of things. So this is dynamic topography, dynamic cartography at work. Something else that you might be able to notice is those two things. They're wildfires. Again, satellite images are used a lot now for this sort of work. And interestingly, you can see, or you can also tell that the wind is blowing from the north in these directions. So these are the sort of inferences we can make to sort of, pull out information from imagery and satellite data. Another example, this is a beautiful image of the Flinders Ranges in Australia. And this is a false color image. So now we've color coded it based on the way the light has bounced back off the surface. And the way the light bounced back off the surface is related to the mineral content of that rock. So this is geological mapping from space. So each of these bands is actually a different geological formation in Australia. And this is a really good way of mapping large areas quite quickly. And in fact, some of my colleagues at the BGS use this exact technique to look for lithium. We all know how important lithium is now in the technology age, to map lithium in Cornwall and South America, in Bolivia and Chile. So these are the techniques we use on day-to-day basis to do geological mapping and find deposits and of interest, commercial and practical interest to us. For me, as a geophysicist, I study the very dynamic aspects of the Earth, particularly things like this. This is a fascinating image taken of the Nyiragongo eruption in the DRC last year. And this image is created by taking a radar image before the eruption and a radar image after the eruption, and then doing a difference. And each of these sort of contours and rings is like a contour of ground movement that has happened in that eruption. So if you were to count each of these rings, so in this one there's about, say, 10 rings, and each of these rings corresponds to around 3 centimeters of ground movement. So on this side alone, on the right side alone, is around 30 centimeters of ground motion that has occurred. And on this side, there's even more. And what we can do, look at these images, that we can tell what's happened underground here. What's happened, we think, is that there's a large sheet of magma, a vertical sheet of magma has risen under the ground and erupted out of the volcano here in this cone in the north. And this short sheet we'll call a dike. And this is equivalent to, say, if you're standing in line shoulder to shoulder and someone pushed into the middle and moved the line apart. This is what's happened. This sheet has moved in and literally forced the ground apart. So again, the dynamic topography now here in this eruption, and it resulted in this spectacular lava flows that really affected the Goma city here, and thousands had to be evacuated. This is a similar image, so same sort of radar difference image, but this time of the Nepal earthquake in 2015. And in this earthquake, again, if you count all the rings, you can figure out that Kathmandu city there moved around 1.2 meters. So the actual capital moved 1 meter, at least 1 meter away from its previous location, which is quite dramatic. Yeah, and all that happened in around 60 seconds. In 60 seconds, the entire capital moved by 1 meter. But the media were more interested in what happened to Mount Everest. So Mount Everest sits on the top right of this image. And in this 60 seconds, the entire mountain moved to the southwest by 3 centimeters. So cartographers beware, you're going to have to put Mount Everest at a different location now. So this is, for me, a dynamic action of the planet. And this is quite exciting. Another, hopefully you'll remember the Japan earthquake of 2010, the magnitude 9. And this was dramatic. It changed the landscape of the world in some ways. Japan is in a fascinating place to study geophysics because the country is peppered with GPS stations. And each one of these little dots here is a GPS station. So this is the GPS network before the earthquake, and this is where the earthquake happened, and this is what happened after the earthquake. So in the earthquake, so if we look at the right image, the whole eastern coast of Japan dropped into the ground by about 1 meter. So the whole East Japan sunk into the ground by 1 meter, and the whole central part of Japan moved into the sea moved eastwards by about 4 to 5 meters. So this is the equivalent of picking up the entire United Kingdom and moving it towards Norway by 4 meters. And all that again happened in about 90 seconds. So the whole location of Japan shifted in that time. So again, cartography, dynamic cartography. And it's not just the topography, and we look at, and my friends and colleagues at the British Antarctic Survey use satellite images to map these things, gigantic icebergs that fall off the edges of mostly in this case, the Antarctic coast. And just to put things into perspective, this particular iceberg is the size of Greater London. And why is it important that we monitor these things? Because these things break off Antarctica and move it into the Southern Ocean. And the South Atlantic is a busy shipping lane. So we want to know where these things are, and how they form, how they die, how they eventually get destroyed before they start impacting on the shipping lanes. And with increasing climate, and this is a worry. And Satellites enable us to do this. Again, another form of dynamic changes on the surface of our planet. This is particularly interesting because my family are from Bangladesh, and this is the Padda River in Bangladesh, otherwise known as the Ganges. And this is what's happened to the river over the last 30 years. And if you look at the scale here on the bottom, that white line is 10 kilometers. So this is how dynamic this river is on the scale of years. And for me, this is amazing. This is just the natural behavior of rivers. But if I zoom into here, that there on the banks of that river is a primary school. So this is where the dynamic nature of the Earth's geomorphology impacts on people. And for me, that intersection is fascinating, especially when it comes to hazards. It's not just natural changes. This is, again, this isn't cheating. It's not from space. It's a LiDAR image from a plane, but it's an image of a dense jungle in Guatemala. But beneath that jungle is this megalopolis city, Mayan city, that has been hidden away for centuries. No one realized this city was there until they took a LiDAR images of it and stripped off all the trees. And beneath all those trees, you find this 60,000 buildings, homes, walkways, roads, a city hidden away that we've only recently uncovered. And this is similar to what Peter was talking about, using LiDAR in the UK, I should say. Something else I'm really interested in is poverty, is how can we use images to understand poverty? And this is the nightlight image of East Asia. Just to context, that's Japan, Tokyo, that's China, Shanghai, and that is North Korea. So if I zoom into this, you see that's Seoul in South Korea, the capital of South Korea, which is the bright mega city. That's the capital of North Korea, Pyongyang, and that's the demilitarized zone. So despite what you might see about all their nuclear ambitions, North Korea is extremely poor. It's so poor that it can't even light itself. It's energy poor at night. So this for me is a proxy for poverty. And I find this sort of proxy is quite fascinating and interesting, and what we can do with them. And you can see on the north here, the border with China. So what else can we do? So again, this is not LiDAR, similar to what Peter showed with LiDAR, but this is photogrammetry using satellite images of the eastern margins of Santiago city in Chile. And once you strip off the buildings and the trees, beneath all the buildings and roads, you find these little bumps on the edge here. And to the earthquake geomorphologist, what you'll see there is that's a tectonic fault there, right on the eastern margin of the fault of the city that 10 years ago, they did not know about. So this city sits on the edge of an active tectonic fault, and they didn't know about it until 10 years ago. So this for me is the real interest of seismic hazard and people intersect. So now we know where the fault is, we can look back at past images in the 1970s and 2014. So that 70s image is from one of the NASA spies, not NASA, US military spy images. And this 2014 is more recent image. If you look into those circles, you notice that in the 70s, that was just a plain hill, and these are just fields. And now these are hugely built up areas right on top of this active tectonic fault. So this is, just mapping increased risk to earthquakes. Another very interesting, I did my PhD in Turkey, so this is one of my favorite examples. In tectonically speaking, Arabia is pushing northwards into Asia by around 10 millimeters per year. And that sort of tectonic motion has resulted in this huge mountain belt in Iran called the Zagros. But on the western side in Turkey, it's caused under what I call the toothpaste effect. And if I zoom in, I'll show you what I mean. So these are the GPS stations in Turkey, and it shows this absolutely beautiful anti-clockwise rotation of the entire Turkish peninsula into Greece, simply because Arabia is pushed in to the east and squeezed the entirety of Turkey out. That's like dropping a hand on the edge of toothpaste and it all squirting out. This is what Turkey is doing on the equivalent of geological timescales. But 30 centimeters per year, 40 millimeters per year, sorry, it doesn't sound like a lot, but in 30 years, that's a meter. So the entirety of Turkey will have moved into the Mediterranean by about a meter in 30 years' time. So we need to update our maps. And this results in lots of earthquakes, is another topic for another question, discussion. Something else my colleagues are doing is, I don't know how I'm doing the time, right? Is looking at, asking the question, how much stuff, concrete, rods, bars, all that stuff, how much stuff do you need to grow a city? It's a fascinating question. We're trying to address this in Hanoi, in Vietnam. And my colleague has done this fascinating exercise. I've looked at past satellite images and characterized how much of these cities, Hanoi here is in this red blob here next to the river, how much of that was built up and how much is it built up now? And building up this time series of how much concrete surface, artificial surface has grown in Hanoi. And you can build up this time series from 1972 to now and show how much of is Hanoi growing. And what we do with that is we map that growth with the mineral resources that city has recorded of using. And then we calculate, okay, that's the amount of mineral resources that we require to grow the city by this much. The city wants to continue growing by this much. How much more material will it need? So these are the sort of byproducts of the detailed mapping we can do. Something else we do a lot as a
2 minutes to go.
Okay, sure. Is respond to disasters. So this is a tsunami in Indonesia. We mapped the coastline changes. So the red here is the old coastline. And now obviously blue is the new coastline. So the parts of the coastline disappeared in the tsunami. So this is dynamic changes to the ground. Something else my colleague has done is look at volcanic eruptions in the sea. So this is Krakatoa, you might know of. This is the volcano before the earthquake, the eruption. This is the volcano after the eruption. Half of the volcano disappeared in one cataclysmic eruption just in 2018. But since then, it started growing. In fact, it's grown by more than 10% of its original size. And we can map this growth using these satellite images. And finally, something I'm particularly interested in is sinking cities. This is Bandung in Indonesia. And we can use this timeline of satellite images to map how much the ground has been moving around the city. And we can show that the city itself is sinking into the ground by around 10 centimeters every single year. And why is this? It's because they're pumping water out of the ground and the whole city is sinking into that space left over. And they're pumping water to feed their textile industry. And these textiles are made in Indonesia and then shipped to Europe. And this is where I'll end my talk. Thank you.